Welcome! In this presentation, we'll dive into LeetCode problem number 658, find k closest elements. This problem challenges us to identify the k closest elements to a target in a sorted array while maintaining their original order. We'll explore multiple approaches, analyze their trade-offs, and understand how to efficiently solve this problem. Let's get started. In this problem, we are given a sorted array of integers called ARR, along with two other integers, k and x. The goal is to find the k closest integers to the value x from this array. The output should be a list of these k integers, sorted in ascending order. Now, an important detail here is that the value x may or may not exist in the array. Additionally, if two numbers are equally close to x, we choose the smaller number. For example, if both 4 and 6 are at the same distance from x, we would include 4 in the result. The input format consists of the sorted array ARR, the integer k representing the number of closest elements to return, and the integer x, which is the target value. The output will be a list of integers representing the closest elements, sorted in ascending order. Looking at the first example, the input array is 1, 2, 3, 4, 5, k is 4, and x is 3. The output is 1, 2, 3, 4. Why? Because the four closest numbers to 3 are 1, 2, 3, and 4. These numbers are already sorted in ascending order, so no additional sorting is needed. For the second example, the input array is the same 1, 2, 3, 4, 5, but this time x is -1. Since -1 is less than all the elements in the array, the four closest numbers are simply the first four elements of the array 1, 2, 3, 4. Again, these are already sorted. Now consider the third example. Here, the input array is 1, 3, 5, 7, 9, k is 2, and x is 6. The output is 5, 7. The two closest numbers to 6 are 5 and 7 because their distances from 6 are the smallest. Specifically, the distance from 6 to 5 is 1, and the distance from 6 to 7 is also 1. Since these numbers are already sorted in ascending order, we simply return them as is. This illustrates how we handle cases where x lies between elements of the array. There are a few constraints and additional notes to keep in mind. First, the size k will always be between 1 and the size of the array n, where n can be as large as 10,000. The array is guaranteed to be sorted in ascending order, and all its elements are unique. If k is equal to the size of the array, the entire array is returned as the result. When determining closeness to x, we calculate the absolute difference, abs, ARR, I, x. For ties, when two numbers are equally distant from x, the smaller number is chosen. Finally, efficient solutions to this problem often use binary search to minimize time complexity, which is crucial given the constraints. To tackle the problem of finding the k closest elements to a given value x, we first considered a brute force approach that sorts the array based on the distance of each element from x. The intuition here is straightforward: calculate the absolute difference between each array element and x, and then sort these differences. Once sorted, we can simply take the first k elements and sort them in ascending order to maintain the problem's requirements. While this approach is simple and easy to implement, it comes with a significant drawback in terms of efficiency. The sorting operation itself takes n log n time, and additional space is required to store the differences. This makes the brute force method impractical for large arrays, especially when k is small compared to n, as the entire array has to be processed regardless of the size of k. Recognizing the limitations of the brute force method, we explored an optimized approach that combines binary search with a sliding window technique. Here, the idea is to take advantage of the fact that the input array is already sorted. Using binary search, we can quickly find the position where x would fit in the array. Once this position is located, we initialize two pointers, one to the left of the position and one to the right. These pointers define a sliding window that we adjust iteratively by comparing the absolute differences between x and the elements at the two pointers. The smaller difference determines which pointer to move until the window spans k elements. This method significantly reduces the time complexity to O log n plus k, by limiting the binary search to log n and the sliding window adjustments to k. Additionally, it requires constant space, making it more efficient than the brute force approach. Another optimized solution that we considered leverages binary search in a slightly different way by directly finding the left boundary of the k closest elements. Instead of focusing on identifying individual elements, this approach narrows down the search space to the starting index of the k-element subarray. The search space is limited to the range 0 and k, which ensures that the subarray does not exceed the array bounds. During the binary search, we compare the differences between x and the potential left boundary elements to decide whether to shift the boundary left or right. Once the left boundary is identified, the subarray from this index to index left plus k contains the k closest elements. This method is highly efficient, with a time complexity of O log nk plus k, and it avoids the need for additional data structures, making it a clean and space-efficient solution. After evaluating these approaches, we chose the binary search on window bounds as the best strategy for this problem. It offers the most efficient time complexity and eliminates unnecessary computations. The key observation that makes this approach so powerful is that the k closest elements, being continuous in a sorted array, can be identified by pinpointing the left boundary of the subarray. This insight allows us to avoid calculating distances for all elements and bypasses the need for sorting altogether. By focusing only on the left boundary, we minimize the search space and achieve optimal performance. Additionally, since the array is already sorted, the resulting subarray is guaranteed to be in ascending order, so no further sorting is required. These observations were pivotal in selecting this method as our final approach. We ultimately selected this approach because of its efficiency, scalability, and simplicity. In terms of performance, it outshines the brute force method by avoiding the overhead of sorting, and it is faster than the sliding window approach for large inputs. Its scalability makes it well suited for handling edge cases and large arrays, as it operates within minimal time and space constraints. While the implementation requires a solid understanding of binary search, this complexity is offset by the method's clarity and its ability to directly determine the subarray bounds without iterative adjustments. Compared to the sliding window approach, this method is easier to reason about, as it avoids manual expansion of the window. The only trade-off is that beginners may find the binary search mechanics less intuitive, but the improved efficiency and elegance of the solution make it the clear choice for this problem. To solve the problem of finding the k closest elements to a given value x in a sorted array, we need to ensure the result is sorted in ascending order, with smaller elements taking precedence in case of ties. The key idea is to use a binary search combined with a two-pointer approach. First, we initialize the binary search by defining two pointers, low and high. The low pointer starts at 0, and the high pointer is set to len, k, which represents the farthest possible starting point for a valid k-element window. Our objective is to locate the starting index of the k-element window that contains the closest elements to x. This initialization sets the stage for efficiently narrowing down the search space. Now, we perform the binary search to determine the optimal starting index for the k closest elements. While low is less than high, we calculate the midpoint, mid, as the average of low and high. We then compare the distances of the two boundary candidates of the k-element window, the start of the window, mid, and the end of the window, mid plus k, relative to x. If the distance from x to mid is greater than the distance from mid plus k to x, it means the optimal window lies further to the right, so we adjust low to mid plus 1. Otherwise, we adjust high to mid, shifting the search space to the left. Once the binary search concludes, low will point to the starting index of the desired k-element window. At this point, we extract the subarray from low plus k, which contains the k closest elements. Several key insights make this approach efficient. First, the use of binary search helps narrow down the range of potential starting indices in O, log, n, time. By comparing the distances of mid and mid plus k to x, we systematically refine the search space to find the most optimal window. The two-pointer comparison ensures that the window is adjusted not only for the smallest absolute difference but also respects the tie-breaking rule that favors smaller values. The sorted nature of the input array is crucial here, as it allows us to directly extract the subarray once the optimal starting point is identified. Additionally, this algorithm relies primarily on arrays and pointers, making it both time-efficient and space-efficient. Analyzing the complexity of the algorithm, the binary search portion runs in O, log, n, as it repeatedly halves the search space to find the optimal starting index. Extracting the k closest elements from the array takes k, as it involves slicing a portion of the array. This gives us an overall time complexity of O log n plus k. In terms of space complexity, the algorithm requires only O1 extra space, as no additional data structures are used. There are also several edge cases to consider. If x is smaller than all elements in the array, the closest elements will be the first k elements. Conversely, if x is greater than all elements, the last k elements will be selected. If x lies within the array range but matches no element exactly, the algorithm still identifies the closest k elements based on their absolute differences. Let's walk through an example with the input array 1, 2, 3, 4, 5, k equals 4, and x equals 3. First, we initialize low to 0 and high to 1, since len, arr, k equals 5 to 4. In the first iteration of the binary search, we calculate mid as 0 plus 1, // 2, which equals 0. Next, we compare the distances, x arr mid equals 3 to 1, which is 2, and arr mid plus k, x equals 5 to 3, which is also 2. Since the distance from arr mid is less than or equal to the distance from arr mid plus k, we move high to mid, setting it to 0. At the end of the binary search, low points to the starting index of the k closest elements, which is 0. Extracting the subarray arr 0:4 gives us 1, 2, 3, 4. The final output for this example is 1, 2, 3, 4. This subarray represents the 4 elements in the array that are closest to x equals 3, sorted in ascending order. The process demonstrates the efficiency and accuracy of the binary search combined with the two-pointer approach in identifying the k closest elements. This code implements the solution to LeetCode problem 658, find k closest elements using a binary search approach. The problem requires finding the k closest integers to a given value x in a sorted array arr. Here's the step-by-step explanation. 1. Binary search initialization. The left and right pointers are initialized to define the search space for the start of the k-sized window. Left starts at 0, and right is set to len, arr, k because the window must stay within the bounds of the array. 2. Binary search loop. The loop continues as long as left is less than right. Calculate the midpoint mid of the current search range. Compare the absolute differences between x and arr, mid, left side of the window, and arr, mid plus k, right side of the window. If x arr, mid, is greater, it means the right side is closer to x, so shift the window right by setting left equals mid plus 1. Otherwise, the left side is closer, so narrow the range by setting right equals mid. 3. Window determination. After the binary search completes, the left pointer points to the start of the optimal k-sized window. The subarray arr, left plus k, is returned as the result. For efficiency, the binary search approach ensures a time complexity of O log nk plus k, which is efficient for large inputs. This implementation is concise and handles all edge cases, such as when x is smaller or larger than all elements in arr or when k is equal to the length of arr. The final result is sorted, as the input array arr is already sorted, and we are simply slicing a contiguous subarray. This is the Java implementation of LeetCode problem number 658, find k closest elements. The logic mirrors the Python solution, with adjustments for Java-specific syntax. Key differences include the use of explicit type declarations, the use of list for the result, and a for loop to populate the result list. The binary search is implemented to find the starting index of the k closest elements, ensuring efficient performance with O log n plus k time complexity. In this example, we are tasked with finding the 4 elements closest to the value 3 in the array 1, 2, 3, 4, 5. To begin, we initialize left to 0 and calculate right as len, arr, k, which gives us 1. The goal is to use binary search to determine the starting index of the closest k elements. In the first iteration of the while loop, we calculate mid as the floor of left plus right, /2, which equals 0. Next, we compare the distances from x to the elements at mid and mid plus k. Here, both distances are equal to 2. Since the left side distance is less than or equal to the right, we adjust right to mid, setting it to 0. At this point, left and right both equal 0, so the loop ends. The starting index for the closest elements is at left equals 0, and we return the subarray from index 0 to 4, which is 1, 2, 3, 4. The result of the first example is the subarray 1, 2, 3, 4. Now, for the second example, we have an edge case where x is smaller than all elements in the array. The input array is 10, 20, 30, 40, 50, with k equals 3 and x equals 5. We initialize left to 0 and calculate right as len, arr, k, which equals 2. In the first iteration of the while loop, we calculate mid as 1. We then compare the distances of x to the elements at mid and mid plus k. The distance from x to arr, mid, is minus 15, while the distance from arr, mid plus k, to x is 45. Since the left side distance is smaller or equal, we update right to mid, setting it to 1. In the second iteration, mid is recalculated as 0. Again, we compare distances. The distance from x to arr, mid, is minus 5, and the distance from arr, mid plus k, to x is 35. The left side distance is still smaller, so we update right to mid, setting it to 0. At this point, both left and right are 0, so the loop ends. The closest k elements start at index 0, and we return the subarray from index 0 to 3, which is 10, 20, 30. This is the expected output for the edge case where x is smaller than all elements. In the third example, we encounter another edge case where x is larger than all elements in the array. The input array is 1, 3, 5, 7, 9, with k equals 2 and x equals 12. We initialize left to 0 and calculate right as len, arr, k, which equals 3. In the first iteration of the while loop, mid is calculated as 1. Comparing distances, we find that the distance from x to arr, mid, is 9, while the distance from arr, mid plus k, to x is minus 5. Since the distance from the right side is smaller, we update left to mid plus 1, setting it to 2. In the second iteration, mid is recalculated as 2. Again, we compare distances. The distance from x to arr, mid, is 7, and the distance from arr, mid plus k, to x is minus 3. As before, the right side distance is smaller, so we update left to mid plus 1, setting it to 3. At this point, left and right both equal 3, so the loop terminates. The starting index for the closest k elements is at left equals 3. We return the subarray from index 3 to 5, which is 7, 9. This is the expected result for the case where x is larger than all elements in the array. By using binary search, we efficiently narrowed down the starting index for the closest elements in all three examples. In this solution, we use a binary search approach to find the starting index of the k closest elements within the array. The binary search operates on the range from 0 to len, arr, k, where the size of the search space is determined by the length of the array, n, and the number of elements we want to find, k. By having the search space with each iteration, binary search achieves a time complexity of O log n k. Once we identify the starting index, we slice the array to extract k elements. This slicing operation, which creates a new list of k elements, takes O, k, time. Together, these two steps form the foundation of our approach, balancing efficiency in searching and retrieving the result. Combining the binary search and slicing operations, the overall time complexity becomes O log n k plus O k. Which term dominates depends on the relative values of n and k. If k is much smaller than n, the logarithmic term, O log n k, is more significant. On the other hand, if k is large and approaches n, the slicing operation, O k, becomes the dominant factor. On the space complexity side, the binary search itself operates in place and does not require additional memory. The only extra space is used to store the result, which consists of k elements. Therefore, the overall space complexity is O, k, reflecting the size of the output list. To understand how this binary search approach compares to a brute force solution, let's break down the naive method. The brute force approach involves three steps. First, calculating the absolute difference between x and each element in the array, which takes O, n. Second, sorting the array based on these differences, which takes O, n log n. And finally, selecting the first k elements from the sorted array, which takes O, k. This makes the total time complexity O, n log n. Additionally, the brute force method requires O, n, space to store the sorted differences. In contrast, the binary search approach avoids sorting altogether. It directly identifies the starting index for the k closest elements, reducing the time complexity to O log int k plus O k. The space usage is also more efficient, limited to O k, for the result list. When assessing the best, average, and worst cases for this approach, the time complexity remains consistent. In the best case, the binary search efficiently evaluates midpoints, requiring O log int k time, and slicing to extract k elements adds O k. The average case follows the same pattern since the binary search is deterministic and doesn't depend on input distribution. Even in the worst case, the binary search still performs logarithmically, having the search space at each step. The slicing step remains linear in k, ensuring that the total complexity is O log int k plus O k across all scenarios. Mathematically, the binary search complexity arises from having the search space repeatedly, which reduces the number of iterations to log n k. Slicing the array to extract k elements directly contributes O k. Together, these operations form a highly efficient solution, significantly outperforming the brute force approach for most input sizes. When solving this problem, there are some common mistakes that can trip you up if you're not careful. First, some people confuse the concept of closest with the numerical value of the elements. This happens when you sort the array by the value of its elements rather than their absolute distance from the target X. This is incorrect because the problem explicitly requires sorting based on the distance from X. To fix this, make sure to use abs, x as your sorting key. Another mistake is neglecting the original order of elements when distances are equal. If two elements have the same distance to X, the one that appears earlier in the array should come first. To address this, include the value of the element as a secondary sorting key. Finally, a brute force approach like sorting the entire array by distance and slicing the first k elements is inefficient for large inputs, with a time complexity of O n log n. For better performance, use optimized techniques like binary search or the two-pointer method to reduce unnecessary computation. Another common issue is misinterpreting the required output format. Instead of returning the k closest elements in their original order from the array, the problem expects the result to be sorted in ascending numerical order. To avoid this mistake, ensure you explicitly sort the result before returning it. Additionally, there's the challenge of off-by-one errors when setting your binary search bounds. These errors can lead to infinite loops or missed edge cases, especially if the pointers low and high are not updated correctly. Binary search requires precise handling of indices, so it's important to double-check the initialization of your bounds and their updates during the search process. Paying close attention here will save you from a lot of debugging headaches. To succeed with this problem in an interview setting, it's important to understand the underlying concepts and be ready to justify your approach. This problem combines elements of binary search, sorting, and greedy techniques. You should be able to explain why you chose a particular method and discuss its trade-offs. For example, using binary search to locate the closest element, followed by a two-pointer expansion, is highly efficient with a time complexity of O log n plus k. Alternatively, a heap-based approach is valid but comes with higher memory overhead. Problems like this often require balancing distance metrics with maintaining the original order, so mastering this will prepare you for similar challenges. Don't forget to consider edge cases, such as when X is smaller or larger than all elements in the array, or when K equals the size of the array. Lastly, solving related problems like minimum size subarray sum or kth smallest pair distance can help solidify these concepts. There are also alternative approaches to consider, each with its own trade-offs. The two-pointer technique involves starting with the entire array and shrinking the range until only K elements remain. This method has a time complexity of O n, making it straightforward to implement, but it's less efficient for very large arrays compared to other methods. Another option is the heap-based approach, where you maintain a max heap of size k to track the closest elements. This has a complexity of O n log k, and is easier to implement if you're comfortable with priority queues, though it does require extra space. Finally, the binary search with a sliding window is the most efficient method. Here, you use binary search to find the starting index of the k elements and then return the subarray. This approach has a time complexity of O log n plus k, but it requires careful handling of indices to ensure correctness. Each of these methods has its strengths, so choose the one that fits the problem constraints and your familiarity with the techniques. And that wraps up our discussion on LeetCode problem number 658, find k closest elements. We covered the key algorithms, their complexities, and important takeaways to help you approach similar problems confidently. Thank you for watching, and don't forget to like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!